So the first question I'm going to raise now is, how do we understand the effectiveness of averaging a crowd? Let's take the Galton experiment. And let's say that the true weight of the ox is X. This number could be any positive number and follow a certain distribution. So we'll soon be talking about the expectation of error relative to the distribution of this X. But everybody got some error term, which could depends on the actual weight X and also differs from one person to another. We call this the estimate Y sub I for the ith participant in the experiment as a function of X. So this is an additive error model of the estimate provided by each person. And let's say there are n of these people. So I goes from 1 to up to n, say 787. And we're going to assume that these error terms are both unbiased and independent. Unbiased means that the expectation of this error term for each user I as a function of X taking over the distribution of X is 0. So sometimes you may overestimate, sometimes you underestimate, but you will not systematically over or underestimate. This holds for all users I. That's unbiased. Independent means that this error term only depends on I. It does not depend on any other user J. In reality, neither unbiased nor independent assumption is true in general. We often see bias, systematic bias. Certain people tend to overestimate while others tend to underestimate. And sometimes these errors are also dependent. In fact, in lecture 7, we'll look at example of information cascade where the dependence of estimates destroys the wisdom of crowds. Now, for Amazon review, actually, is it unbiased or independent? It's actually not unbiased. Okay? Although you may be able to use user ID and history of her rating to do some normalization. And it's sort of independent. Most people enter review based on her own opinion. So even if she can see the existing rating and reviews, she may not be reacting response to them, but sometimes they do. Sometimes a review says that the previous reviews are certainly biased. I'm here to correct that. So there is also some element of dependence on Amazon. All right, so now we're going to look at the so-called wisdom of crowds, exemplified by Galton's experiment, by comparing two terms. One is the average of errors made by each individual participant. The other is the error of the averaged estimates. And the hope is that the error of average estimate is much smaller compared to the average of the error. Let's first look at the average of error. That's easy. The error term clearly is epsilon I for participant I, and we're going to use L2 norm or mean squared error, just like last lecture for Netflix, except over there we use a root mean square. Sometimes we take the square root, but the idea is the same. We're going to use the squared error as the metric to quantify error terms. So we'll look at this thing squared, and then we'll look at the expectation of this term over the distribution of X, and then we'll sum over all the participants from 1 to n, take the average by dividing over n, and this is what we call the error term for the average error. Okay, or averaged square error to be more precise. So just remember this expression. This is the averaged squared error. On the other hand, we also want to look at the error of the average. First of all, what is the average? Well, average is the sum of yi's divided by n. And the error of the average is that minus x. Okay, so it could be positive, could be negative. This is the same as 1 over n times sum of yi minus n times x, obviously. So we can also write this as the sum of 1 over n times summation of yi minus x. By bringing x inside the summation here, because there's a factor of n, we're okay. And this is just 1 over n times the summation of errors, because each term inside the summation y minus x is just epsilon I by definition. So now this error of the average is what we want to look at, and we're going to look at this error of average as the expectation over distribution of x of 1 over n summation epsilon I, this whole thing squared, which equals 1 over n squared. Can take that out of the expectation times the expectation of the summation epsilon I x, summing over I, this whole term squared. And you say, look, this expression, isn't it the same as the last expression? Looks like saying there's n summation expectation epsilon squared, but not quite. This is taking the sum of the expectation of squared epsilon, whereas this one is the expectation of the square of the sum. So this one is talking about square of summation, not the summation of squares, and the two are clearly different. For example, just two user case, epsilon plus epsilon 2 squared, which is what this is about, is epsilon squared plus epsilon 2 squared plus 2 times epsilon 1 epsilon 2. This is what the averaged error is about. This is the error of the average. The difference is the collection of these cross terms. But if they are independent, then we say that epsilon times epsilon 2, you take the expectation over distribution x of this expression, is going to be 0, because these two error terms are not correlated with each other. So these cross terms are cancelled, and in that case, sum of square and square of sums are the same. And therefore, this expression is the same as this expression. So the only difference is the multiplication factor in front of it. In this case, it's 1 over n. In this case, it's 1 over n squared. And therefore, we have the desired relationship. That is, the error term of the averaged. You average first, then you look at error, is actually only 1 over n of the error term if you look at the averaged error. So compute error first of individual ones and then take the average, versus average first and then look at the error term. These two are different by a factor, multiplicative factor of n. And this multiplicative factor of n is often codified as an example of the wisdom of crowds in Galton's experiment that says simple averaging can work if it's unbiased and independent estimates. There's no bias terms, and these cross terms cancel each other under the expectation of distribution of x, and we have effect of n enhancement. If there are 5 people, it's 5 times better. If there are 1,000 people, it's 1,000 times better in terms of the mean squared error. Now, what if they're completely dependent? Then we don't need these calculations at all. Whether you average first and then look at the error of that wisdom of crowds, or you just look at the average of the individual errors, it doesn't matter. They are the same. If they're completely dependent. If they're somewhat dependent, then you have to look at the expectation of these error terms correlation in more detail, but it will be somewhere between a factor of 1 versus a factor of n, or 1 over n, depending on how you look at it. This sounds very promising and encouraging. With a simple derivation which seems to be able to identify the root cause of the wisdom of crowds. Well, let's look at the positive side before we look at some cautionary remarks. The positive side says that as long as they're independent of each other, then you have the wisdom of crowds. This particular type of wisdom has nothing to do with identifying who's the expert. It just says that you might be wrong in all kinds of directions, but as long as you are wrong in different directions, then we will have the power of this factor of n, enhancement of the error term. In hindsight, it's hardly a surprise. This is really the law of large number plus the convexity of convex quadratic function at play here. Now you may object first, what if I actually know who are the experts here? Maybe she's a farmer. Well, in the advanced material, we'll look at how we can use boosting methods to extract the more important opinion by the experts. There will be a very different philosophy. This philosophy, in what we just talked about, only depends on the fact that you can all be wrong as long as you're wrong in different ways, independent of each other. Now, second objection is that what about the scale? This factor of n effect holds even when n is 2 or when n is 1,000,000. To most people, the wisdom of crowds means that there should be some threshold value n star above which you see the effect, below which you don't. But this one applies just as well to two-people case. So that's some mystery that remains to be resolved. The third objection, or I should say addition to this discussion, is that this factor of n is only one view on wisdom of crowds, what we call the multiplexing gain. There's another view called the diversity gain that says if there's some bad events you don't want to happen, then by putting n of these entities together, you get 1 minus p bracket to the power n, where n is again the size of the crowd effect. This is called the diversity gain. This is called the multiplexing gain. We will encounter this diversity gain in later chapters. In fact, we encounter both kinds of gains in the wisdom of crowds in both technology and the social networks, between wireless networks on your Wi-Fi LTE network all the way to Gallatin's example. But this is our first encounter on one side of this coin.